I'm not sure what will be on the exam, but once you announce the exam like that, a date, I'm really reluctant to change it because people start making plans, and inevitably there's one person who is working and arranged at a company not to ship them over, to Boston that week because, and then if they would change it, but, study guide meaning, yeah. Knowing everything sounds great, right? Any other questions? Well, we have 2 more faculty candidates coming this week. One tomorrow and next one on Friday. They're both giving their talks at 11 o'clock, and they're both security positions. So we'll be talking about the research and security. And the good news, at least for me, is then that starting next week is going to free up a lot of my time to actually like do grading and things like that. I'm definitely looking forward not to have to spend hours doing email on to candidates and then spending half my day going to talks and lunch and dinner and moving around. But as much as I like to go out to dinner, I like to get my work done too. So what I want to do, timing is probably not the best, but talk about some clustering. I was going to then talk about doing decision trees and random forests, but I decided to do that later. So I think you've been patient with me enough talking about all this, analysis stuff, and then it's time to get on to Spark and start seeing what that's all about. So after we talk about clustering, we'll start looking at Spark. Partially, yeah. And so it's likely we'll be talking about Spark on Thursday. So clustering, I can remember which light is the right one to turn off. That one, okay. Clustering is an unsupervised learning. I mean, you basically say, here's the data, find me the clusters, right? Find me how things cluster together make groups. And so then we can categorize things, right? So groups in similar ways. So all these points belong to this group, and this group. And then when we get new data, we say which group does it belong in, right? And again, using a library like scikit-learn or any other libraries out there, basically once you've got your data set up correctly, you call a function to fit the data, and then you just say, here's more data, tell me which group it belongs in, right? So the actual doing it is not that hard. It's understanding what it does for you and the limitations. And yeah, I mean, there's all kinds of reasons why we do clustering. Bioinformatics, you're doing sequencing, and you want to group them in different. I want look at all these genes and how are they similar, how are they different, right? Okay, so we'll create a bunch of clusters for that. Market research, right? I mean, you interview N people and ask them give them surveys, and then you want to, what can we do? These people fall in the groups. If they fall in the groups, and then we can predict what they're going to do. And once we do that, then we get new people. We can say, okay, here's what we expect them to happen. And this group, well, we think represents 40% of the population, so maybe we should listen to them. And yeah, I mean, it's all kind of image processing. Okay, I mean, we want to divide them into regions that represent borders. So we've got borders, not borders. And now here's some more pixels. Are they borders or not borders? Yeah, all these recommend, you've all done this, right? You go to the website, we recommend you buy this, right? We recommend you, buy this or listen to this song based upon your previous, how do they do that, right? Which means somehow they've taken your past buying history, your past listening history, and then used that to see what group you belong into, and then decide, okay, this group likes these type of tunes, or people who bought this history often buy this, right? So you need to group people by, the purchases, what they listen to, etc. And we've looked at Bayesian classifiers. We'll look at clusters today. Later on, we'll look at decision trees, and we're probably not going to talk about neural networks. We get a whole course on neural networks, and they're far more complicated. Again, once you have a library which does it for you, you can just say, "Here's my data." But there's a lot more tuning you typically have to do in neural networks. And it's just, you have a bunch of points in space, and then we're going to figure out which ones are close to each other. And then, once you say we're going to take points that are close together, what do we mean by close, right? What's the distance? We're used to, well, the Euclidean distance, right? Is like I start here, and let's see, I get one, and the diagonal, so I can, just, but that's not the only way to talk about distance, right? For example, if you have text, how are text, what does it mean for two sentences? Are they close together or far apart? What does that mean? And then, we saw earlier, right, when we're looking at, price and weight, and then, is the price in US dollars or is it in, right, Mexican pesos? That price can affect, the scale, right? And that can then affect what things are close or not. Particularly if you have a bunch of stuff and you take one axis and you really draw it out, then, things which are close here, they're farther apart, and they get farther apart, they might now be closer to something above which before they weren't close to, or relatively close to, right? And so here is, just a list of different ways we can measure distance, right? And Euclidean is, well, there's two Euclideans, right? But then, city block, okay, we know what that means, right? You just can go left or right, but I mean, and yeah, Hamming distance, some of you may have heard of because you do codes, and that becomes important. But there's a whole bunch of different ways in which we measure distance, and they then help us understand the data a different way. And just, right, if I have Euclidean distance, right, is just, I mean, you take the 2 points and you take the difference and you square it and sum it all up, and so that becomes, from there to there is 2.83, right? The city block, I mean, it's 4. I mean, right, you have to go 4 blocks to go from one square to the other. Hamming distance, well, how many coordinates you have to flip, right? And it's just 2, but it's also 2 for this, right? Cosine distance is like, well, what's the difference, the cosine between the 2 vectors, right? And so going from 2, 0 to 0, 2 is just that cosine of that's 1, but going from 2 to 0 to 10, 0 is that's 0, right? Because there's no angle between them. And so there's different ways of measuring these distances, and that can affect what the cluster tells us. And also, depending on the scale of the data, right? Like I said, if we take our data set and then we just multiply the x-axis by 10, right? That could change the clusters that are formed because it changed the distance. Look at what are close to each other, right? And if we've got can I do this? Maybe I can do it. Where can I do it? Basically, if we got a point here and a point there and a point here, right? And we start asking what points are close to each other, these 2 are close to each other, right? And so if we're creating a cluster starting here, we might add this one to that one, right, to form our cluster. But now if I stretch out the x-axis, right, this one may get way over here. All of a sudden, oh, wait, these 2 are closer than that, so we would start adding a cluster this way, right? And so that can affect what clusters we form based upon the distance. Yeah, so there we can take your music and put it in categories, right? And then we group them by categories and look at how many music you listen to in each different category, and then compare it to other people. And so then say there's 100 categories, and then we can your listening habits become a vector, right, of how many tunes or songs you listen to in each category. And we do that for everyone. Now it's just vectors, right? We can also just do it categorically. And decision trees allow us to do that. Basically, we just go through and we also haven't, well, there's a regression. The logistic regression is used when we just have categories. And so then we can also use that regression to try and so here are some different ways of normalizing data. Min max is so the max min. When data gets spread out, we can divide by the large range of the data, and then make the minimum go to 0, right? So from 0 to 1. So if this is my data set, right, then it'll compress data between 0 and 1. So the smallest number gets mapped to 0 because we're going to take the minimum and subtract it off every data point, right? And then we're going to divide by min divided by the max. And so, this is what we get. So we get everything between 0 and 1. So it compresses it down. If I add a really large number, what happens is, right, the numbers are close together, get squashed together further, right? Standard mean deviation. Why do people do that? Well, what does standard deviation tell us, right? If I go, how many standard deviations to go from the mean to get like 90% of the data? Yeah, it's like 1.96, right? But after it goes certain far, we're getting most of the data, right? So it sort of tells us, standard deviation sort of tells us how spread out data is. So divided by the standard deviation is going to try and squash it down based upon how far it is spread out. And then subtracting by the mean is going to center it at 0, right? And so usually it's pretty hard to get 3 standard deviations out. That's a pretty rare event. So almost everything is in between -3 or 3, but there could be a few outliers. So we take something, again, same data set, and it gets mapped to, right, a smaller range, and the distance between them changes. And having an outlier really affects it. That one outlier is going to change the standard deviation quite a bit. This takes care of the outliers and maps them to sort of maximum point. So adding that 2,000 really didn't change the other values much. It just squashes it down to 1. And basically, this is that curve. And so once you get beyond a certain point, all the values are about the same. It pretty much gets rid of your outliers. The sigmoidal and the logistic function are often used in neural networks. The problem is your neural networks, you basically feed them data, right? Here's a picture of a cat. Here's a picture of more and more cats. But each neuron in your network has to decide yes or no, right? And so these functions are often used as a way of, okay, this is a range I'm going to say yes, and everything else I'm going to say no, right? And it helps take care of, these weird outliers, right? So if you get something, if you feed it cats, right, and then you're going to show, a truck, well, it's going to be completely different, right? So it's going to follow the range, and so this makes it easy to say, okay, no, right? My vote is this is not a cat, but something weird. And I don't know, are there any sports fans in the class? I know there's soccer fans, right? So the ELO system is a way of, of ranking teams based on the performance, and they use as a way of helping rank them in terms of what happens when you got a really good team and they just get slaughtered by or lose to a really poor team. How do you deal with that? Chess. Yeah, my chess days are long gone, and so I'm used to the point system where each person gets points, and then when you beat something, there's a formula that tells how many points you get, how many they lose, and again, just mapping that data set, right? So there's also two parameters, and that's also means there's two parameters you get to tune your algorithm with, which is always can be useful, but also can be a problem in that the more parameters you have to tweak with, the more it is likely you can just keep on tweaking your parameters until the model does what you want it to do, which may not be the right model, right? It's just like if you've got enough parameters and you tweak enough, you're finally going to find a setting which will work for that particular data set, right? It may not be a good representation of what the actual underlying process is. It just, here's my data set. Literally, if you've got n data points, I can find an n plus 1 polynomial which will go through them all, right? That doesn't mean that polynomial represents the underlying process. And the technical term is overfitting, right? We overfit the model. But again, when we start adding, the large number, it really doesn't change the other numbers that much, right? It's all arranged and just map it all to. And yet we can start fiddling through this, but it's again, and I always run out of time because whenever I come across something like this, like, well, what happens when I do this? What happens, right? To get some feel for what it means. You can see it can really change, right? Here it's 0.7, and here it's 1.6, right? Really, it's a. And when you do a neural network or something, you can tune, right? And you can tune it differently for each neuron. And what does that mean for the model? And again, there's one of these creative formulas that people come up with to try and adding this large number, right, changes standard deviation, so it moves all the points around. So yeah, they all move somewhat, and they also got all these closer together based on that outlier. This is fun, right? For text, right? So there's several things you need to do. One is normalization. And so, yeah, there's tokenizing the words. And then there's the punctuation. You get rid of punctuation. There's all these non-text characters that occur. Oh, and then it's fun when you get the text, right? And you get the end of the line, and there's a long word, and then what do you do with that word? Oh, you break it, put a hyphen, and then, oh, but then some words are always hyphenated, right? And then you decide, okay, do I remove that hyphen or not? Do I keep it in? What do I do? And then there's all these A's and ands and thises and that's. And then there's all these stem words. I mean, how do you, so it's, what's that? Right. And then there's some languages, they don't put space between words, right? A sentence is one long string of text. Right? Thai is like that, right? It's like entire sentence, no space, period, space, then next sentence, right? So tokenize that will be fun. Basically, in English, basically you just like, okay, there's space and punctuation marks and hyphens, and then we can, but in Thai it's like, no, you have to, as you read it, you have to recognize, oh, this is the word, right? And that's a token. Yeah, and all these stem words, right? And then you get things like this, right? I mean, sleep and sleeping, okay, that's easy, right? We look for ing, okay, take that off. Slept. And so you actually need a dictionary, right? Of, here are all the forms of this word. And people have done that. And there's, in Julia world, someone in C wrote this program a long time ago to deal with English, to worry about this, and they just incorporated it. I was surprised not to see that in Python, to actually convert all this words into stem words, so you can then just worry about that. And then what does it mean? How can we talk about distance between words, right? So one way we can do it is this. I have no idea who Jacquard was, but given two sets, he or she defined this measure of how far the sets are apart, right? So it's basically, take the intersection of the two sets, the size divided by the union, right? And so always get between 0 and 1, because both are positive numbers, and so you can't get negative. And the intersection of two sets is always going to be the same size or less than the union, right? And so we can do that with words, right? We can basically take two sentences and we can treat them as sets of words by, to tokenize them and do all the, and so here we get, A and B, jar distance is 0.667, and, C, it's 1. Now, A and C you can see, right? Because there's music, musical, lovely, love, and then there's all this. But the middle one doesn't make any sense, right? It's because we're talking about war and locomotive history. The problem is we have all those is and those, and right. Now, if we normalize the text, right, the distance between A and C goes down, because now lovely and love become the same word, right? And music and musical become the same word, right? So they become closer together, and then this distance gets farther apart. The other way to deal with it is, again, we can convert into vectors, right? Now in this case, right, we can get rid of all those crazy, and then just create vectors, right, based on that location, and then we get, right, these vectors. And now there are different ways in which, since they're vectors, they go into, in this case, a six-dimensional space, right? So we can then treat them in different ways, right? One way is just treat them as regular vectors, right, and take the Euclidean distance. One problem with Euclidean distance is that, if you have a sentence that contains the same word over and over again, right, that may put it farther away from a sentence which has almost always the same words, right, which not good. So one way to deal with that is to use the cosine distance, right? Take those two vectors and take the cosine of their angle. That way, when we got, two sentences which have a lot of the same words, but some of the words are repeated many times, right? And so that vector is going to be far, and then it's going to be like this. The angle doesn't change, right? So then we start looking at, here, this distance becomes larger, and this distance becomes smaller, right? Yeah. So that said, we now talk about clustering. There's a number of different algorithms to use for clustering. Center-based, and then there's this density cluster, and k-means is perhaps the most common clustering. Almost every library has it. It's pretty straightforward. And how does it work? Well, basically, remember, these are unsupervised, so we don't tell the algorithm. We don't say, here's a cat, here's a cat, here's a cat. We say, here's the data, figure it out. And so what it does is, what we do have to do, we tell how many clusters we want, right? So say we want, in this case, okay, I want 3 clusters. Here I can say 3 because I can plot and say, yep, there looks like there's 3 clusters. And so what the algorithm will do, it'll pick 3 random points and say, okay, those are going to be the centers of my clusters, right? And then you start looking at all the points and say, which center are this point closest to? It goes to that cluster, right? So you do that for all of them. The problem is it may have picked 2 points from here and 1 point from there, right? But it will get 3 clusters. And then what you do is you look at basically the center of those clusters and pick those as new points and repeat the process, right? And you keep on repeating until basically things converge. And sometimes it doesn't converge, right? And sometimes this is not going to work well, right? And we'll see some other examples where the algorithm will just fail because it just can't find it. Some implementations of the k-means allow us to select which starting points to use, what points in the data to use as our, right? And if we have this data, we could plot it and we say, well, let's pick one of them, right? And then, of course, if the data is n-dimensional, and the dimension is more than 2, you're probably not going to be able to do that. So you pick k points, one for each cluster, and each data point that's closest to that cluster, you add to that cluster, and basically readjust the k points, and it depends upon whether you're which algorithm we're dealing with, right? If we're doing k-means, right, you pick the middle value in each cluster. Nearest neighbor, we do something slightly different, but the same algorithm. You pick some points, put them together, and then and one difference is between these two is your center an actual data point in the cluster, or can it be just any random point? Yeah. The third one is you could pick any random point, right? It doesn't have to be one of the data points. And so what k-means is, yeah, the algorithm, you just select k points, and then you grab every point in your data set, and it says, which center is this closest to, and you put it in that cluster, right? And when you're done with that, you compute the mean of the cluster, and that becomes the new mean, and now you repeat the process over and over again until basically it settles down. And scikit-learn, if it doesn't settle down, it'll say, okay, it didn't converge under this many iterations, so you can add more iterations to go longer. And that doesn't solve the problem, then you have a different problem to solve, right? And so the example is here's, so I pick those 3 points, right? And then these become my clusters. And then we can pick the mean of each cluster, and then we repeat the process to get different clusters, right? And then pick the mean again. Well, we pick the mean again. We keep on repeating that until things settle down. Because, these 2 points really belong in that cluster, right? Because at least that one does is a lot closer to this center than right. So the matter is, we actually pick a data point. It has to be the center of our cluster. And the second distance is usually you can add a distance matrix which defines what it means for these two, how far apart these points are, right? Whereas the k-means is just Euclidean distance. The k-means is nice because well, how do you find the point in the cluster that's nearest the center? So you have to compute the center, right, and then find which one's closest. With the k-means, you already done when you computed the mean of all the data points. So here is, right, there is this famous training data set. And so using k-means of 3, then it converges really nicely because the clusters are pretty well defined, right? The only difficulty you have is these boundary points, right? It's not clear you know, that point, where should it really be, right? Now, the problem is what happens when, I mean, the data is nice. I mean, we know it's 3 clusters. What happens? We don't know the number of clusters. Yeah, so it's like picking initial points, number of clusters, how good they are, right? So the same data set, picking different number of clusters. So when I said there's 2 clusters, I said there was only 2, so it did 2, right? And some of these data points is like, that's weird, right? Why is that one way up there, not part of this cluster? But when you do 4, right, I mean, it has to divide a cluster into 2 parts, right? So we get that one divided, did 5, now I get 2 divisions. And the division in number 5 is different, right? Because here it's like that, and here it's like that. And, so again, 6, even if you do this 6 to 7 second time, you get a different set of clusters. Why? Well, because you're picking different starting points, right? 3 times 6, we get different results. Because then you're picking different starting points. Right. There's a couple of metrics people have come up with to try and measure this. One is silhouettes. Unfortunately, when I was putting structure together, I couldn't find silhouettes in the cycle. I was like, what are you guys doing? I mean, come on. But then last night I found it, but it was too late, right? And also using it is a little complicated because you basically compute the silhouette of each point in your data set, and then you plot all those values. And then what that plot looks like, how separated they are, gives you some measure of goodness. There's also another metric called the Dunn metrics, D-U-N-N, that people use to, again, try and come up with some way of numerically trying to figure out whether it's a good cluster or not. And the problem is here, I mean, like, we know the answer, right? But yeah, I mean, we didn't need to run the cluster algorithm to know there are 3 clusters and what the clusters were, right? So you know that in real life. I mean, if you got this, you don't need to run the cluster algorithm, right? Only time you run the cluster algorithm is when you don't know, right? And once it's 3 or 4 dimensional, I mean, forget it, right? 3 dimension, you might be able to plot it and do the rotation thing, but 4 dimensions, you're gone. The problem with this set, right? Using k-means is even if you pick a point here and pick a point here, it's not going to work, right? Because if I pick a point here, all these points are close to that point, and they're that point. It doesn't matter which point you pick in here, you're never going to be able to detect that as a cluster and that as a cluster, right? So you start getting, divide in half, right? And clearly this is like, forget it, that's the wrong cluster for that data. I mean, there's clearly two clusters here, one in the middle and one outside. Here's another fun example. So scikit-learn has a number of data sets to use to illustrate points. One is make moons. So it creates these two moon-like shapes, and then you can indicate how many items you want in each moon, how much noise to add to each moon to make it tighter separated. And then this is basically a random number to start with. And so you can specify the same number each time to get the same result, which is useful. And so here I just plot it, right? Clearly there's two clusters. Clearly, k-means is not going to work, right? Right. So here's when you try to do the k-means, right? It makes sense. If we start a point here, it doesn't matter whether point you, I mean, it just can't work, right? Because these points are closer to things in here than, right? And they're closer to the things over here. Right. So these algorithms make certain assumptions, right? Your data is convex, right? Because you pick a point in the middle, right? And then we're going to, and other points. And so we're building circles around them, which basically means or spheres or n-dimensional spheres, you know what, right? And you need to know what k is. So scikit-learn has SpectralClustering, which uses k-means. But what it does is, some of you have heard of this trick, the kerneling trick. Basically, what we want to do is we're going to apply a transformation to our data, so to change it somehow. So ideally, we would take, perhaps map these in 3 dimensions to get them farther apart. But it worked, right? I mean, not sure how many people are familiar with this local minimum problem. If we use a greedy algorithm and say, here I want to find the lowest point in the line, right? So one standard way of doing that is called the greedy algorithm. You pick up random point, right? And, okay, so I pick this point, and then you say, okay, you look at, and you want to go, which way should I go? I want to find a minimum, so I can go up or down, so I go down, right? And the problem is, when I come to here, it's like, okay, if I go this way, I'm going up again, wrong way, and so we stick here. We never go find that. How do you avoid that? Well, you pick different starting points, right? And then see the result. So you have to repeat many times to, right, see if you can find. And if I pick 20 random points to start, I have some probability of finding, right? So then we have to look at, if we're finding the smallest point, we would run the experiment 20, 30 times, and then across all of them, we pick the one which is smallest. And hopefully we picked some point between here and here, the starting point one of those times, and then we find a true local minimum. But for clusters now, it becomes, we have to pick different starting points, right? And the hard part is, if I'm trying to find the point where this line is lowest, I have an easy to compute metric to tell me what the result is, right? Just run the experiment 100 times and take the minimum result. I'm done. How do we measure the quality of a cluster? The DBSCAN, that's what it stands for. Density-based spatial clustering of applications with noise. And it's relatively new. And it operates in a completely different way. There's two parameters to the algorithm. One is distance and one is min point. And now we can find some terms. A core point. A core point is a core point if there are at least that many points within this distance of the point, right? And that including itself, right? So the question is, are there lots of things close by, right? And we get to define what close by means and lots means. Next one is directly reachable points. So if I start at a point, if I start at a core point, right, then all the directly reachable points are that our distance from a core point. So I start with my point, and okay, I can go out that distance and then see are there any other core points there. Okay, and then each one of those points, I can go up that distance, right? And all those points are then reachable, right? So I look at all my core points, and it's reachable if I can go from that point and I get all core points, right? And then I go to epsilon, and all those points are reachable, right? Because if I've got a and Q is reachable from P if there's a path, right? So I can start going bing, bing, bing. Start at one point, look at all the points that can reachable from there, and then those points are reachable from there, right? And then all those points, I keep on going until I get from P to Q. And then outliers, any point that I can't get from these core points. And the way you form clusters, the cluster is going to be a core point and all the points reachable from it. That becomes a cluster. Right, so here's an example where our min points are going to be 4, and so what happens? Well, I take this one, I look at this distance, and there's 4 points. So okay, so that's a core point, and the same thing happens here, right? Those are core points. I look at this one, right, and oh, there's 1, 2, 3. Here's my 4th. This one, we've got 1, 2, 3, 4, right? So that's a core point. But this poor guy is not a core point, right? Because there's only 2 points his neighbor. Same thing here, right? So these all become core points, and then the yellows become reachable, and so then this is one cluster, right? Too bad, right? He's out in the middle of nowhere. So, right, we don't have to worry about picking cluster points or number of clusters. I mean, it'll figure out for ourselves. We determine that distance. We determine that how dense we need things to be. And it's pretty fast, n log n. Varying densities, yeah, this area is really dense, but when we go over here and it's less dense, then we may choose a small distance because of this one, and then over here it's like can't find anything because they're too far apart. So that's why varying densities don't work very well. The problem with that is the higher dimensions you get, the further away things get, right? So the density gets very thinned out. And so then you have to pick really large distances and pick that very small, and then all of a sudden everything becomes a cluster. So here, again, just fiddling with the different parameters, right? Needed 10 points and a distance of 6, and it actually found different clusters, right? So it found the main clusters, but then it's like, what do we do with all that stuff, right? But it never really, you couldn't reach them, right? They weren't reachable. What isn't necessarily bad, because it tells you those things are outliers, right? And maybe do they really belong to a cluster or not? They could just be sometimes you run across weird things, right? And increase the distance a little bit. And as they start increasing the distance and keeping them in points, right, those outliers tend to go away, because now we can actually get to them from a and ta-da, it works, right? Yep. Yep. Not that I'm aware of. That it's basically the number of points and the distance, right? And because it's going to build a cluster all by itself, right? Because it's going to find all the core points, and then it's going to find everything you can reach from it, and that becomes your cluster. And this leads us to the more dimensions you have, the farther apart things get, right? If I got one dimension on the unit square, so it's just from 0 to 1, it's only farthest part you're going to get is 1, right? On 2 dimensions, I can go from 0, 0 to 1, 1, right? And that's farther away. And then when I get to 3 dimensions, I go from 0, 0 to 1, 1, 1, right? And that just keeps on growing, right? And then if you start picking 2 random points in n dimensions, the higher dimensions get, the farther the average distance becomes. And that becomes a problem for many algorithms. It also, the more dimensions you have, the more data you need to actually be dense enough to do something with. So there are processes we can use to actually get rid of some of our dimensions, right? And a common idea is, look, when we're looking at data, sometimes the variation in the data is really concentrated, right, in a few dimensions. And so those are the important dimensions. The other dimensions may not play much of a role. So can we find those dimensions which have most of the variation of our data? So here's an example, right? It's like, oh, that really looks like it represents a line, right? But it's in 2 dimensions. So if we take our axis and rotate it, right? And now what we can do is we can take and project our data onto that 1 dimension. And now we're going from a 2-dimensional space into a 1-dimensional space. And we haven't lost too much information, right? And so, right, people should know this already, right? Principal component analysis. Here the idea is what we want to do is we want to find the dimension with the greatest variation, right? And then find the next axis, which has the next, until we get down to a point where, okay, we can, the rest of the stuff we can just throw away because it doesn't add too much to the data, right? And then we just pick those first k dimensions and work with that. And so we've gone from a k dimension, or n dimension to k dimension. And also, then we can actually transform that data in different spaces, right? So this is one website which gives you different examples graphically to show it. And so they say, look, given these data points, right, it's really a line, so we can select this coordinate system and then project the data points onto, right, this axis, and we haven't lost much. But what does it mean to say we haven't lost much, right? And again, we're dealing with data which is obvious, right? And so what they're saying is, yeah, project it into this coordinate system, and now line, and we can just project it onto that axis and treat it as one-dimensional data. And if we project this data on the x and y coordinates, it's all scattered, right? If we project this one on the new axis, right, you know, that is pretty well spread out here, but on this new, right, y-axis is hardly any, it's all concentrated in one spot, pretty much. So basically, transform this into this axis, right, and then just get rid of y. And just, now it becomes one less dimension. So, another one of, right. It depends on the algorithm, but some data, right? Using, well, so we're creating random number generator. We're creating which axis it should go on, and then generating a bunch of points. And this dot product then, I mean, this range is small, and so we're going to blur it out a bit. And then, of course, there's a function called PCA, and you just tell how many components you want to reduce it to. And then you fit the data, and then you can say, give me the components. And it gives you the two vectors. We can ask for the variance, right? So it's telling you how much variance on those axes. And so there's more variance, right, on the first axis and less on the second axis. So it gives you a feel for how much variance is on the second axis. That it also gives you the mean, so you can then translate to that point, and then, right? And so this data, right, here is the long axis and here's the short axis, and this the length is determined sort of a indication of how much variance is on. I ran it on one of the moons, and for some reason I get the second axis plotted, but it's that was the major axis that it's selected. Now the data was two-dimensional, right? And I said two components because I wanted to know the variation of each one, right? And that's how the funny line was drawn. And then how to create one moon. Right? So it's some basics about clustering. It's not a course of machine learning, so it's not as detailed as you would get there. Then we'll start talking about Spark on Thursday. I'm not sure how much. Well, when I talk about Spark, I'm going to talk about both in PySpark and using Scala. Well, we'll talk more about the motivation for that on Thursday. Yeah.